One of the problem types I like to ask in the integration section of the course involves these problems. We actually saw some of them on exam 3. I think I used capital B there. I'm going to switch because I don't want the capital B to be confused with option B on the multiple choice. So I'm going to start using capital M as an unknown constant. And so the idea is this. This is an expression in x, it's an expression in x, but it also has a variable m. And this definite integral is given to be equal to, in this case, 22. And our problem, our task then is to find the value of m, which we could substitute into here to make this a true statement. And what happens is we're going to do the calculus, and then when we're finished with the calculus, we're going to end up with an ordinary garden variety equation that we solve using our basic algebra skills. I like these kinds of questions for a couple reasons. Among them, my understanding is this kind of thing actually can arise on standardized exams, exams for entrance into engineering school, graduate exams. So these kinds of problems arise because they're just a little bit different. They make you think differently. So our task then is to do the calculus, but set this as equal to 22, carrying that all along, and eventually we're going to get a simple little equation to solve in m. So we're given that this expression, the integral from 0 to 2, definite integral from 0 to 2, 12x squared plus 6mx, 6m is the coefficient, minus 3 dx, that's equal to 22. So this implies we do the calculus. The antiderivative is 12x to the third over 3 plus coefficient is 6m x squared over 2 minus 3, reattach the variable indicator, and that is evaluated from 0 to 2. Now remember, these limits of integration are x values. Just for emphasis, you don't need to do this, but just for emphasis, this is x equals 0 to x equal 2. These values get substituted for the x's, not m. M just comes along for the ride for now. We know this expression is still equal to 22. And so what does that imply? Well, first I'm going to simplify this. This is 4 x to the third plus this becomes 3m x to the second minus 3x, and that's evaluated. I'm going to go back to just 0 to 2. And that's equal still to 22. And so what do we get? We evaluate at the upper limit of integration minus evaluate at the lower limit of integration, but that is still equal to 22. We're just given that 22. All right, so what do we have here? Substitute the upper limit of integration. So this is 4 times 2 to the third plus 3m times 2 to the second minus 3 times 2. Now 0 is particularly easy because 0 to the third is 0, 0 squared is 0, 0. So this just becomes 0 plus 0 minus 3. If this had been some value other than 0, minus 0. If this had been some value other than 0, you would need to actually substitute in and get another expression. Notice this expression is now in terms of m. If this were not 0, this would be an expression in terms of m. And so now we're going to create an equation involving m. This is 2 to the third is 8. 4 times 8 is 32. This is 2 squared is 4 times 3 is 12m minus, that's 6. This falls out because coincidentally they're all 0. But that's still equal to 22. And all we have to do now is solve for m. So do the calculus, and now append onto that a little piece of algebra here at the end. Let's see, 32 minus 6 is 26, plus 12m is equal to 22. Subtract, I believe, the 26 across. Is that what we need to do? Subtract the 26 across. And so 12m is equal to 22 minus 26. And that is negative 4. And then divide the 12 out. So m is negative 4/12. I'm okay with that. If you don't like 4/12, you can change that to negative 1/3. And so m equals negative 1/3 is what's required to make that expression true. All right? So, take a look at that. It's straightforward. There's the calculus portion, and then what you inherit from that is a basic little algebra portion here. I have a couple other examples like this, that some of them involve derivatives, some of them involve integrals, and so we'll just kind of work through a few of those here. So the next example, which is similar to this, this one involves a derivative. Let's see, so we're given f of x is equal to 12 natural log of x plus 2m x to the third. And we're also given that f prime of 2 is equal to 18, find m. So we're given the derivative evaluated at 2 is equal to 18. So what do? You find the derivative, you evaluate it at 2, set it equal to 18, and back solve for m. So just do what you're told to do. Do the calculus portion, the derivative. So first, we need to find just the derivative, because we have the derivative evaluated at 2. Find the derivative, evaluate it at 2, set that equal to 18, and then back solve for m. So the derivative here is straightforward. Constant multiplier multiplies along, and the derivative of natural log of x is 1 over x. If you want, you can write that as 12 over x. And then this is the power rule. 2m is the coefficient. So the derivative of 2m x to the third is 6m x to the second. So we know that f prime evaluated at 2 is equal to 18. So what does that imply? If I plug 2 in for all these x's, that must get equal to 18. So I have 12, I'm going to write this as 12 over 2 plus 6m times, this is 2 to the second, and that's equal to 18. Back solve for m. So that's, what's that, 6 plus, that's 4. 4 times 6 is 24. And what do we have out of that? So that implies, subtract the 6 across, 24m is equal to 12. And so that implies m is equal to 1/2. All right. So do the calculus and just retain that unknown constant, unknown coefficient, and then establish what you've been given to find, and that'll allow you to back solve to find the value for m. All right. Let's see. We have a couple other examples of that. And so here is our next one here. Let's see. It says this. It says there are 2 values of m which make this There are 2 values which makes this expression true. One of them is m equals 0. What is the other? And the expression is this, the integral from -1 to m. So now m is the upper limit of integration. That's fine. It's a value. It's a number that's in the domain. So m is the upper limit of integration, and this is we have 18 x to the second plus 6x dx, and that is set equal to 3. All right. So here's our problem. This is the integral. Definite integral from 0 to m. I'm sorry, from -1 to m, -1 to m of this expression, this integrand, dx is equal to 3. So we're given that. And it says there are two values of m which make this expression true. One of them is 0. What is the other one? So do the calculus. The calculus says, find the antiderivative. This is 18x to the third over 3 plus 6x to the second over 2. And that's evaluated from -1 to m. Remember, m is the value of the upper limit of integration. But we're given that's equal to 3. So the same thing's going to happen, which happened on our first little example here. We're going to generate an expression involving m. Let me simplify this real quickly here. I want to simplify this on the fly. 18 over 3 is 6. So this is 6m to the third. M, remember, these are limits of integration. So just like before, this is x equals -1, and this is x equals m, right? So m is going to get substituted. The limits of integration get substituted in for the values of x. So 18 thirds is 6. We have m to the third plus 6 halves is 3. And then this is m to the second. All right? Minus, and now evaluate at -1. And so evaluate at -1. This is 6 times -1 to the third plus, and again this is 3, times -1 to the second. And we know that's equal to 3. That whole thing is equal to 3. Simplify all this rot over here on the left-hand side. I'm going to run out of space here if I'm not careful. This is 6m to the third plus 3m to the second. Now what does this become? Be very careful here. This is minus. This is -1 to the third is -1. So this is -6. This is -1 squared is +1 plus 3 is equal to 3. So what do we have? We have this in here. This is -3, but it's -3. Do we see that? -3. So this equation on the left-hand side becomes 6m to the third plus 3m to the second. This is minus -3, which becomes plus 3, is equal to 3. Solve that equation. Well, there's several ways to do that. Probably as good as any is subtract the 3 from both sides and get this thing equal to 0. I'm going to steal some space up here. So if we subtract 3 from both sides, we generate 6m to the third plus 3m to the second is now equal to 0. And the advantage now, since that's equal to 0, we can factor and set them equal to 0. So factor out 3m squared, leaving behind 2m plus 1. And then set each of those to 0. If I set 3m squared equal to 0, we get m equals 0, which is the one we were told about. But what is the other? We get 2m plus 1 is equal to 0, and that implies that m is equal to -1/2. And so there are two values that make this expression true. One of them is m equal to 0. We verified that. What is the other? M is equal to -1/2. All right? Okay, so let's see. I have one more of these examples like this, and I think that's going to be getting you the flavor of how these work out. So we have one more item, and then we'll set you to your task. This is the integral from 0 to e of 4m over 2x plus e. And that is equal to, this is given to be equal to the natural log of 3 of all things. And so the question is, can we figure out what this is equal to? All right? So let's see. So we're given this. Find m. Let's see what we can do with this. So find the antiderivative. Well, here the problem is the antiderivative here requires a u substitution. All right? There is no quotient rule for antiderivatives. So this is a U substitution. The only way we have to do these fraction expressions is U substitution. The only two tools in our toolbox for now are basic forms and U substitution. When you get into Calculus 2, you'll get a lot more tools and a lot more complicated problems. But for now, it's either a basic form, which this clearly is not, or it's going to have to be a U substitution. So I'm going to rewrite this. Well, we can do it this way. Well, let's just let U equal, and I'm going to let U equal this denominator. Remember, E is a constant. So the derivative of U, the differential here, the derivative on the right-hand side is 2 dx because the derivative of this constant is 0. All right? Well, look, I don't want 2 dx. What's the leftover piece I want? This accounts for that part of the integrand. What I have left to account for is 4m dx, which means I need to create 4m dx right here. So the thing I need to multiply both sides of this expression by is 2m. If I multiply both sides by 2m, 2m times 2 is 4m dx, and that is precisely what's left over. The substitution is exact. We can now change the limits of integration. The limits of integration are upper, so here's my limits. The upper limit of integration is u is equal to 2 times the limit of integration goes in for x. Well, 2e plus e is 3e. And the lower limit is x equals 0. So this is 2 times 0 plus e, which is just 1 times e, or e. So now we can substitute, and this implies, well, this is now equal to, by the substitution, this is now the integral from e to 3e, and this is the value u that's in the denominator. This entire expression is the differential. I need 2m. I'm going to put this constant multiplier out front. And so I'm left with 2m times 1 over u du. So do the calculus. Let this m just come along for the right. And we know that this entire expression is equal to the natural log of 3. So this is now an implication. This equation implies this equation because of the substitution. So now let's do the antiderivative. The antiderivative of 1 over u is the natural log of absolute u, but this is now evaluated from e to 3e. And that's still equal to natural log of 3. All right, just continue to the left-hand side, continue to the antiderivative, evaluate the upper limit of integration minus evaluate the lower limit of integration. Because these expressions are positive, the absolute value may be suppressed. We may ignore the absolute value. So this is 2m times, what do we have here? We have the natural log of 3e minus the natural log of e, and that's equal to the natural log of 3. So far, so good. Evaluate this expression. Evaluate this expression. Again, I'm going to steal some space. This is 2m times. Now, this is a tricky bit. When you subtract the logs, that becomes the log of the quotient. When you subtract the logs, that's the log of the quotient. There are a couple of ways to do this. One way to think of it is it's just the log of the quotient. And so this is, remember our rule that says natural log of let's say a minus natural log of b, that's equal to the natural log of a over b, right? And so I can express this as the natural log of 3e divided by e. So this is the natural log of 3e over e. This isn't the only way to do this problem, but this is as good as any. And that's still equal to natural log of 3. And so what do we get out of that? Well, the e's cancel. So we're left with 2 times m times, what are we left here? That's the natural log of 3, is equal to the natural log of 3. And this is convenient because now divide out log 3, divide out log 3. By the way, the calculus is now over. As soon as you find this expression, the calculus is over. This is now remembering your glory days from back in algebra somewhere. And so what we have here is the natural log of 3's cancel. So we're left with 2 times m is now equal to 1, which implies that m is 1/2. So there's plenty there, but if you keep your wits about you, do the calculus part first, and then just solve what you have left over from that whatever you inherit from the calculus will be an expression in terms of m, and then solve that using the skill that you have from basic algebra coming into the calculus sequence. So that's a sketch of several of those varieties, and I think if you keep those in mind, you should be able to handle anything that I'm going to throw at you.